Jai Hind. Today our topic of presentation is instance-based learning. In instance-based learning, we are going to cover introduction, what is instance-based learning. Then we'll discuss classification and regression methods in which we do instance-based learning. One method we'll discuss is k-nearest neighbor, that is KNN method for classification. And then we'll talk about the distance weighted KNN, and then we'll talk about the application of instance-based learning to regression. And finally, we will compare our lazy learning and eager learning. Lazy learning is done in instance-based cases, and eager learning is when we do other methods, like if we do SVM, we calculate linear regression, logistic regression, or neural network. So when we talk about instance-based learning, what is our idea behind? We will store all the training examples. So what is our aim? We will only store the training examples. For example, I am having input xi and the function is fxi, that is the output. So what we are having our all the training examples that we will simply store. So what the idea is, in instance-based learning, we'll see the instances stored, and when a query comes, so let me take the query as xq. When a query comes, then we take the action, then we do the calculation and we find the answer, that is approximate function, the class in case of classification and the real value in case of regression. So one method is nearest neighbor. What nearest neighbor says, when we are given a query xq, we will locate the nearest training example xn. So what will be class of our query? That will be simple, the class of xn. We will find the nearest neighbor, that is our nearest neighbor method. And another version of this is k nearest neighbor, KNN. What we have in KNN? In KNN, when a query is given, we'll take k nearest neighbors. When we will take then these k nearest neighbor, then we'll say what is the maximum result, what is the maximum class. So simply we can say we'll take the vote among these. If let me say I am having k examples and in those k examples maximum are belonging to positive class, then our query will belong to positive class. If maximum are belonging to negative class, then the query will be classified as negative. The second is real valued. If I am having real valued problem, so in real valued, what we will have, we will take mean of f values of k nearest neighbor. In case of classification, we will find out what is the maximum number of classes and we will assign the query point according to that. And in case of regression, in case of real valued, what we will take, we'll see the k nearest neighbor and we will find out the mean value. So this is sum of all the outputs of output values of k nearest neighbors will sum up and divide by k, so we'll get the mean. And in this case, in discrete valued, we will have the number of instances, number of classes, which is maximum. So this is the idea, that what idea is, in instance-based learning, we simply store all the examples and then we see the nearest neighbor. If the nearest neighbor, when we find the nearest neighbor, the output function will be same as the nearest neighbor. If we are having KNN method, k nearest neighbor, then we will find out the k nearest neighbors, and according to that, we will decide it belongs to which class or what is the real value answer. So first question, when we start with the nearest neighbor, when we start with instance-based learning and nearest neighbor, so what to consider? When should we use it? We apply the nearest neighbor when we are able to map the points in n-dimensional real space, Rn. that is r cross n times. So if n is the dimension, I will present that in n dimensional space. And it is advisable that we are having 20 attributes per instance. Then we can go for nearest neighbor. It will give us an efficient answer. If we will have more than these attributes, then it becomes very slow. When we are having lot of training data, then also we can prefer nearest neighbor, because it is based on the nearest methods, nearest points which are drawn in the Rn, that is n dimensional real space. What are the advantages of nearest neighbor? In nearest neighbor, when we do training, what we do, we explicitly do not calculate the target function. We simply store all the data points, that is our examples. So that is the fast training phase. The training is very fast because we are not explicitly learning any target function. We are finding the class or the regress value according to neighbors. So it is able to learn very complex function and there is no loss of information. And what is a disadvantage when we are applying nearest neighbor? Because there is no calculation done at training time, everything is calculated at query time. At query time, when a query comes, the distance of this query from all the points will be calculated to find the nearest neighbor. So it is having much calculation at the time of query. So it is slow at query time. And what is another point to be noted in case of nearest neighbor? When we are having, let me say, 15 attributes, sometime all the 15 attributes are not relevant to the classification. But what we do in nearest neighbor, we consider all the attributes and we find the Euclidean distance from each and every attribute, and then we decide what are the nearest neighbor. So our classification may get fooled by the irrelevant attributes. So now, starting with the method of KNN, what is nearest neighbor method algorithm. Before that, let us discuss the concept of Euclidean distance. In nearest neighbor learning, the target function may be either discrete valued or real valued, as we have seen on the previous slide, that we can have a real valued output, or in real valued we take average of the neighbors, and it can be a discrete value, that is the classification. In case of classification, we will see that how many are belonging to which class. So we will take the majority class votes, where it will be majority class, then we will whatever will be the majority class, that we will consider for the classification. So now what is our instance? How to find the Euclidean distance? Let my instance is x and it is having the feature vector a1x, a2x, anx. Means a1x. What is a1x? a1x is first attribute, that is a1 of x instance. So arx denotes the value of rth attribute of the instance x. So when we find the Euclidean distance, we will find the Euclidean distance between two instances. Let me call it xi and xj. The distance is represented by d xi xj. What it will be? We will take the difference between rth attribute of xi and xj and will square that. So now what is rth attribute? All the attributes one by one will consider. So here it is shown that arxi minus arxj whole square, and what is the value of r? R is 1 to n under root. So this is the Euclidean distance formula that we use to find the nearest neighbor when we apply the nearest neighbor instance learning method. Now our algorithm. So now let us discuss the algorithm for classification first. So what we want to do? We want to learn a function f. What we want? We want to learn a function f which is mapping n-dimensional real space to V, where V is my set of classes. What is V here? V could be V1, V2, V3 up to Vs, as I am taking as number of classes. So we can have this number of some class from this. This is our finite set. So this is discrete valued. So now let us discuss the algorithm of nearest neighbor. So what is our training algorithm? In training algorithm, explicitly as such, we do not learn the target function. So what is our training phase? Our training phase is very simple. What we do in training algorithm, for each training example, x, fx. It means for each input and output pair, add the example to the list training example. What we will do? Simply we will make a list of training examples and we will store all the examples there. So that is, for each training example, simply add the example to the training, all the example to the list training examples. Now, when the classification is done, so that is our second part, classification algorithm. We are given a query instance xq. xq is our query instance. Now calculation will take place. So what we will do, let x1, x2, xk denote the k instances from training examples that are nearest to q. What does it mean? It means we will do the calculation of Euclidean distance, and from there we will find out the k nearest neighbor and we will denote those as x1, x2 up to xk. These are our k nearest neighbor in the training examples for a given query. So all the calculation has been done at the query time. During training phase, we are not explicitly learning anything. We are deferring the calculation till the point when a query comes. That's why we call it lazy learning. In other methods, we calculate like linear regression or decision trees. What we do, we calculate the final explicit function for the given training examples in advance before the query comes. But in this, everything is calculated, every work is done when query comes. So actually we are deferring the calculation of the complex function, that is our target function, till the query comes. So this is lazy learning. So now we have calculated the k nearest neighbor. Now see what we will do. Now what will be the answer? Answer will be the class which is having majority votes. It means we will see the neighbors and which class is occurring maximum time in the neighborhood, that will be the class of the query. Okay, so what is our function here? What we will return? What will be the returned class? That will be argmax v belongs to v. It means for each possible class, we will calculate the number, the count. What we are using as count here? That is delta function. What delta function is saying, if the given class and fxi both are same, if the given class and fxi for each given class, let me say I am having two classes, true or false. So for true, I will check the k nearest neighbor. If the function in that k, one of the nearest neighbor is the true, yes class only, true class only, positive, then we will take one count. Okay, otherwise we will add 0. If the classes for which we are calculating the number is matching with the given instance class, then we will add 1 to the count. So that's why delta AB is taken as 1 when A is equal to B. When these are not same, for which class we are calculating, then we will simply add 0. So this way what we will get the final count of each class, and which class will be returned, which will have the maximum value, and that will be the class of the given query. Let us try to understand this with an example. Here we are taking k is equal to 3, and what is given? We are given two attributes P1 and P2 and the class is given. So how many instances are given? We are given 4 instances, 1, 2, 3 and 4. What are the instances? The instance x5 belongs to false class, 7, 7 belongs to false class, 3, 5 to true, 2, 4 to true. So this is our given set of instances we are given. So we are given here 4 instances. The 4 instances are 6, 5 with false class, 7, 7 with false class, 3, 5 class is true, and 2, 4 instance class is true. Now what is given? K is equal to 3 and query point comes as 4, 6. Query point is 4, 6. Now we have to classify 4, 6. Will it be false class or will it belong to true class? So what we will do? We will first calculate the nearest neighbors. Now what is our count of nearest neighbor that we are applying here? What is KNN? That is 3. K is equal to 3. So we will find out the K nearest neighbor, means 3 nearest neighbors. So I am having 4 instances. From these 4 instances, I need to find out 3 nearest neighbor instances. So with 4, 6, I will apply the Euclidean distance. 4, 6, 4 minus 6 whole square plus 6 minus 5 whole square. So I am getting here 2, 2 square is 4 plus 6 minus 1, 5, 1 square. So I am getting in answer under root 5. So what is the Euclidean distance of query 4, 6 from first instance? 6, 5 is under root 5. Same way, when we are calculating it with 7, 7, so we are getting 4 minus 7 square plus 6 minus 7 square. So what answer we are getting? Under root 10. With third instance, we are getting the distance as under root 2. With 2, 4, I am getting the distance as under root 8. Now when we compare it, we see the descending set. So what we want the minimum distances. So here if I consider under root 10 is the maximum among all. So we will not count it in nearest 3. Nearest 3 will be minimum, that is under root 2, then next minimum, this, then next. So we have calculated, we have taken 3 instances. So these are our neighbor instances, x1, x2, x3. So among these are x1, x2 and x3. We have taken the 3 nearest neighbors. Okay, now what the algorithm says? Algorithm says that when we have got these 3 nearest neighbors, what we need to do? We need to find for each class the count, and we will find the count and we will return for which class argmax, means the count is maximum. So what was our formula? We were having delta function. Delta function was calculating the value for count for the classes, how many occurrences are there. So what are our occurrences? We are having 2 occurrences here, false and true. So when I make a count of false, so I can see that it is matching, first output is matching. So I am having 1 count. These 2 are not matching. So we will, the delta value will be 0. So 1 plus 0 plus 0. So this is for false. So what count I am getting for false? That is 1. And when I am taking the second class is true. Now my delta function will be delta true comma the output of the class. For first it is not matching, so we will have 0 count. For second it is matching, so plus 1. True is matching with third one, so plus 1. So how many occurrences are there? 1 for false and 2 for true. So which need to be returned? Argmax, which is having the maximum value. The maximum value is true. So the class of the query, that is 4, 6 will be taken as 4, 6 will be taken as true. So simply what we did, we took k value as 3. We found the Euclidean distance from the given query point. When we got all the distances, we select the minimum 3, and from these minimum 3 we counted how many are of false class and how many are of true class. Here we have seen that the true class instances are 2 and false class is 1. So we will assign 4, 6 query to 2, that is with the majority weight. So this is our k nearest neighbor method. Now when we are discussing nearest neighbor method, k nearest neighbor we have done, one example we have done. Now our question is, actually we are trying to learn some target function. We are not learning it explicitly in the beginning and then applying the queries. No, we are calculating that function only when query comes with the help of the neighbors. Okay, so now question arises, when we are doing this algorithm, when we are considering it, actually what is our hypothesis space that we are searching for? So the major point to be noted here is, the k nearest neighbor algorithm never forms an explicit general hypothesis f regarding the target function f. It doesn't consider in hypothesis that I will consider linear function or we will consider quadratic or Gaussian, whatever we are talking about, we will not consider that. It simply computes the classification of each new query instance as needed. It is not considering initially any explicit general hypothesis. So now, because it is not explicitly, that's why we say it lazy learner. Now the point comes, okay, we are not considering in advance the hypothesis space, but actually what it is providing us? What type of shape it is providing? Is it providing us linear one or some other? So that question still arises, still remains here. So this can be, in case of nearest neighbor method, this can be answered with help of Voronoi diagrams. The diagram shows the shape of this decision surface, which is induced by one NN. It means we are considering only nearest neighbor. Whatever will be the nearest neighbor, that class of that particular nearest neighbor or output of that particular nearest neighbor, we will assign to the given query. So if we consider this diagram, in this diagram, we can see that if I am having this particular point, so 1 NN, now the point is to which points it is the nearest neighbor. If I consider a point here, let me say this is my point. With this point, when I calculate all the neighbors, this is the nearest neighbor. So which class will be assigned to this? Only of this. Same way for this. For all these points, we are having this particular only the nearest neighbor. So all will get assigned the class to which this particular instance belongs. It means it is considering all the points which are enclosed within this boundary. So that's what we say, that it is able to learn complex target functions. The design surface is a combination of convex polyhedra surrounding each of the training example. For this will be the polyhedra which will be surrounding. So for this, it is learning these boundaries. For this is learning these boundaries. The polyhedron indicates the set of query points whose classification will be completely determined by that training example. So for each training example, we are having a polyhedra and its edges will decide that this will be the class of all the points in this within this particular hydra. Query points outside the polyhedron are closer to some other training example. If I consider this one, it is outside the polyhedra, so it will not take the class of this, it will take the class of this. So that is what we say, that we will consider some polyhedra. So it is because it's not a line, it's not a plane. So we are having a complex target function learned when we did simply nearest neighbor method. So this is our hypothesis space consideration when we are using the nearest neighbor. Now, Another thing that we must understand when we are talking about nearest neighbor is, let us consider some example. For example, if this is the area, this is my query point, and it is nearest to these two neighbors, and it is having these three neighbors as negative class. So here what we have taken, in this area we have taken 5 NN, 5 nearest neighbor. If I consider these 5 nearest neighbor, what will be the class of query? The class of query will be the negative class. But if I see this at first glance, it looks like that XQ should belong to positive class. So what it happened, we consider 5 neighbors, and according to those 5 neighbors we have calculated the class of this particular one, but actually it should be positive. Now why this happened? Because we have ignored the Euclidean distance. We are simply calculating the majority vote, and we are not considering the distance, the Euclidean distance value. We are simply saying, okay, these 3 are nearest, so these will be considered. Okay, so it might want weight nearer more neighbors more heavily. So when we want to weigh nearer neighbors more heavily, then we simply do not use KNN, we use distance weighted KNN. So in distance weighted, we will not only consider that 2 neighbors are positive and 3 neighbors are negative, but we will also consider how far positive neighbors are and how far negative neighbors are. So both the things will be counted, the vote as well as the distance. Okay, now when we said that distance we will consider, so when we are considering distance, so now we can have consideration of all the examples also rather than only few neighbors, because when we are saying that it is based on nearest neighbor, it means what are the class of nearest neighbor, according to that we will divide the query point, we will classify the query points in some given class. Okay, but if we consider distance also and we consider all the points, then automatically as the distance will increase, the impact of the distant points will be lesser when we will classify the query point. Okay, so what is the point here, that we can use all the training examples also. Okay, so if all the training examples are considered when classifying a new query instance, we call it global method, and if we use only the nearest training example, that is K examples which are nearest, then we call it local method. Okay, so what is the difference, how we will do distance weighted KNN? So in distance weighted, what we did in KNN we stored all the examples, so same we will store all the examples. Then in simple KNN, what we did, we took the query, we find the nearest examples, same we will do. Okay, now where will be the difference? The difference will be in the final classification, what we will return. There what we returned in case of simple nearest neighbor, what we did, we used the delta function to see the similarity. Actually, when we found it similar, we counted it as 1. So it was simply returning the count, that as we discussed on last slide, 2 positive example, 3 negative example. What we will do, we will divide that, we will multiply a weight. The count will have some weight and less weight to distant point. Okay, so what will be our count here? Our count will be weighted count, WI. Now what this WI is, the WI will be inversely proportional to distance. So what we have taken here, WI is 1 upon distance square. To avoid the calculation of under root, we have taken here square. So it is divided by distance square. Now as the distance increases, the impact will decrease. Okay, that's why we are taking a weight inversely proportional. The weight will be given, a higher weight will be given to those points which are at less distance. It means less distance, more weight, more distance, less weight. Okay, that is what we want in distance weighted KNN. So now let us understand what we will do here. So we have got, as we have taken the same slide, the same example. So what are our near points? The near points are first, second and third, because these are nearest neighbor. This is having the minimum distance, next distance, next distance. Now what we did when we took the two classes, first is false class and second one is true class. Now what we will do, we will not simply compare false with false and will put count 1, false with true plus 0, false with true plus 0. So what we got here, that is 1. But now what we are having, weighted, we will have weighted count. Okay, so now we will apply WI, it means weight. Okay, so when we are taking weight to this, we will divide it with the distance square. What is distance square? 1 by 5. Now we are not giving a full weightage 1. We are giving the weightage, we are counting according to the distance. Now when we are taking the second class, in second class initially it will be 0 because it is not matching with false, then it is matching with true. So when it is matching with true, it means we have to give one value, delta will give us one value, but will multiply by the weight. What is weight? Square. So 1 by 2 plus 1 by 8, because it matches, and matches means 1 and weight means 8. So it will be divided by 8. So now we are getting it as 0.2 and something here 0.5 plus 0 point something 1, 2 and so on. So it will be something 0.6. So which one is higher again? That is true. So class will be true. So this is distance weighted nearest neighbor. In this we have considered the distance also for better result, better accuracy. So this is our these are our classification methods that we have studied using instance based learning. Now a point may come that our point, which is the query point, is already present in examples. So if it is already present in example, then we will simply take the output as the answer. What will be the output of the query? That is the given output which is present in form of example. And if we are having multiple example with those attributes, then we will again consider the majority classification. When it will be majority, what will be the majority value? That we will take in the output. So this is our distance weighted KNN. So what is our inductive bias in nearest neighbor methods? The inductive bias corresponds to an assumption that the classification of an instance X will be most similar to the classification of other instances that are nearby in Euclidean distance. It is having this bias that the class will be same as the class which are nearby in Euclidean distance. That's why we are calculating the Euclidean distance. So this is all about our nearest neighbor classification. So in this particular lecture, we have talked about nearest neighbor, instance based learning, nearest neighbor, and then we did one version variation of a nearest neighbor, that is distant weighted nearest neighbor. Thank you. Jai Hind.